then all of these zeros are 12 zeros. This is what this 12 means. This is what this 9 means. This is what this 6 means. This is what this 3 means. And what we do is that if we have a prefix, then we are going to go ahead and if we're in the capital T, capital G, capital M, and capital A, K, we're going to go ahead and we're going to multiply them by this value, by 1 trillion, 1 billion, a million, and 1,000. This is what we're going to do when we find these prefixes: a tera, a giga, a mega, and a kilo. Because our unit of measure is going to be the voltage, but it could be in kilovolts, it could be in megavolts, like I mentioned yesterday, and we're talking about high voltages, really high voltages here. For example, for substations, for power generation stations, we're going to be talking in the thousands and in the millions of volts. But then when we go to smaller equipment, like for example a computer, we might be talking about picovolts or nanovolts or millivolts, right? So this would be low voltage. So when we encounter the lowercase m, the symbol, which is like a weird U for micro, the lowercase n for nano, and the lowercase p for pico, we still have the same prefixes. This is still power of 10, but what we're doing here is that we're dividing. So when we have the lower cases, we're dividing by this number, this same number. We use this same number, but when we have our low voltage, we were going to divide. But when we're in our high voltages, we're going to go ahead and multiply by these same values. So we're going to go into the lower decimals, or we're going to go into the higher values for high voltages. Okay, this is what we're going to do when in a mathematical equation we find these types of values. We just go ahead and we do the conversion, because when we have to find the value of amps, we can't use the 470 milliamps. We have to use 0.47 to be able to get a correct answer. That was one of the mistakes that I found in a couple of operations that were done yesterday, that because we had, for example, 1.8 megas, they added them like if they were actually 1.8 ohms, and then we got all decimals, which was incorrect because we were talking about the megavolts. So the step that was missed was doing the conversion from mega to volts, or mega ohms to ohms, milliamps to amps, because we have to do everything in either volts, amps, or ohms. These are just to abbreviate so that we don't have so many zeros there. That's what we use. We use the numerical prefixes just so that we can abbreviate the number and we can have a smaller number occupy a smaller space. Is that something clear? Does anybody have any questions on how to do these conversions? Yeah? Yes?
So for when it's negative, we just do the same thing, but we just divide?
Exactly.
The same number, like it would be like negative 1 million.
Mm-hmm.
Oh.
Negative 1 trillion, 1 million, 1 billion, and 1,000. So we just are going to either multiply, depending on what we find, or we're going to divide.
Oh,
okay? This is a very easy way to be able to make conversions. And if you wanted to abbreviate your answer, you can go ahead and do the same thing in reverse. You can just divide again, and then you're going to have a smaller number, and you can add that prefix. Okay? All right. So we talked about our series circuits yesterday. What are the rules for a series circuit? How would you recognize a series circuit?
Two resistance.
Hmm?
Two resistance.
The resistance,
The same current.
current is going to be the same
Same.
throughout the whole circuit, right? That's one of the ways that we can actually, analyze a series circuit. We know that if I have a circuit that is in series, it doesn't matter if my power source is a battery or is alternating current. When I place a multimeter on a circuit, at every part of this circuit, I should read the same amperage. So for example, if I'm taking a measurement right here, the total amperage of the circuit is gonna be the same here at this part, at this part, at this part, and at this part. Our constant value in a series circuit is going to be the amperage, right? That's a way that we can recognize a circuit that is in series. What would be another way, another very important way to recognize a series circuit?
Add up.
That would be a rule, right? That would be a rule to be able to solve for a series circuit. But another important part of a series circuit is you notice that current only has one path. One path only. So in order to go back to the power source, because we know that a circuit is a closed loop, right? At wherever it starts, if it's starting right here and it's coming back here, it has to make a complete circle. That's why it's called a circuit. It has to pass through resistor number 1 and pass through resistor number 2 and pass through resistor number 3 to be able to get back to that power source. Current has only one path to travel when we're wiring in series. Now this is the reason why we don't wire homes in series. We wire homes in parallel because in this type of circuit, one of the resistors fails, and what do we have there? What do you see there? We have an open circuit, correct? So this would be an open circuit. Exactly. Christmas lights, the old style Christmas lights, not the new ones, but the old style Christmas lights, they were all in series. So what happened when one of the light bulbs would burn and you had 500 lights, you had to figure out which one was the one that burned, and you would spend hours and hours. I remember I saw my mom right there checking all of the lights because one of them had burned, and it was so tedious because you had to figure out which one was the one that opened the circuit, right? Now they don't make them that way. They wire them in parallel because if one of the lights change, you can easily figure out which one it is because that's the only one that's off. All of the rest of them are on. So if you have an extension in parallel that has, let's say for example, 10 lights, this circuit is a circuit that is in parallel. So we have 10 resistors. We have our 1, our 2, our 3, our 4, our 5, our 6, our 7, our 8, our 9, and our 10. All of these are actually allowing current to make that complete circle. So if my current comes through here and it wants to come back to the power source, it can make a complete circle right here, come back to the power source. At this point, it could do the same thing here. It could travel through here and come back to the power source here. So if one of these were to fail, my current still has 9 more other paths to come back to the power source. So that's why if you have 10 lights in your house, all of them are wired in parallel. So whenever one of the light bulbs burn, none of the other ones are affected. You just need to find the one that's burned and changed it, and that's it, right? So this is a much more effective way to be able to wire a circuit in parallel. and 99% of homes are wired in parallel. We will give multiple paths for current to go back to the power source so that our loads are not dependent on each other. So what do we do when we have a parallel circuit? We're giving multiple paths for current to go back, do the work that it needs to do. For example, turn on this load, turn on all 10 loads, and then go back to the power source, right? So in a parallel circuit, my current does not only have one path to travel, it has multiple paths to travel, depending on how many loads I place. If I have 10 lights, 15 lights, 20 lights in one circuit, let's say for example, a big commercial building, I might put 20 or 30 lamps on one circuit, and then I might put another 20 or 30 lamps on another circuit, depending on how many amps the circuit consumes. Now, what happens to amperage in a series circuit?
Stays the same.
It stays the same,
Yeah.
right?
Yes.
Now,
Stays
the
same.
rule for the amperage in a parallel circuit is that amps adds up. So, amperage adds up. In a parallel circuit, the amperage adds up. Now, we do have a constant value in a parallel circuit. Our constant value is going to be voltage. So for example, if I apply 120 volts to this circuit, which is the nominal voltage that we have in a home, I'm gonna go ahead and apply 120 volts to the circuit. Resistor number 1 is gonna receive 120. Resistor number 2, 3, 4, 5, 6, 7, 8, 9, and 10, all of them are going to be receiving the same pressure. So all of them will work at 120 volts. That is why all of your receptacles in your home, they are wired in parallel. So when you take your multimeter and you put it in, you should be reading 120 volts on all of them. They all have the same pressure. But they have a limited amount of capacity depending on how many amps I put into the circuit. For example, what is the amperage capacity of a number 14 wire?
15?
15 amps, right? So let's say that the total amperage of the circuit is 15 amps. I'm running a 14 gauge wire, and this circuit has a capacity of 15 amps. Because my amperage adds up in this circuit, I need to make sure that all of these loads don't exceed 15 amps. Because the amperage of all of the loads in a parallel circuit is going to add up. So I need to make sure that these lights at least consume, for example, most of the lights that we install now consume about 0.089 amps. Now I want you guys to take 15 and divide it by 0.089 and tell me how many lights I can put on a 15 amp circuit. 0.089. So you're gonna take 15 and you're gonna divide it by 0.089.
Like around 16.
Like around 16, right? So am I within the capacity of the circuit?
Yeah.
I only put 10 lights, right? And if I take my 15 amps and I divide it, right? I divide it by 0.089. It tells me that I have a capacity of 16 lights. And I'm putting only 10 lights on this circuit. So this means that each one of these lights is consuming 0.089 amps. Can I add more lights?
Yeah.
I can add another 6 lights, right? Because my circuit has the capacity of 15 amps and I'm barely using about.
Oh, okay, yeah.
Yeah? So this is how we calculate what size of wire are we gonna use in a home, right? What is our load and how many loads are we going to have on that circuit? We do that a lot for lighting. Then for other loads, like for example, receptacles, we can't really do that. The code just gives us a maximum amount of receptacles that we can put on a 15-amp circuit and on a 20-amp circuit, because we don't know what's gonna be connected to.
Is it 0.089 or 0.89?
0.089. 0.089.
Cause if you divide 15 by 0.089, it's 168. It's not 16.
15 divided by 0.089.
Right.
Yeah.
If you divide
168.
15 by 0.89, it gives you 16.85. And if
Which
you
would be
apply the
17.
10%, then you can add 7 more, right?
Mm-hmm, yes.
Yeah.
No, it's 0.089. That's how much,
So,
the lights, the LED lights are consuming. So yeah, you can add a lot of lights, that's why I was telling you.
168.
They're very, very,
168.
very effective now.
it's not 16.
Mhm. So, they don't consume a lot of power now. Before, our lights, let's say one light in your living room would consume half an amp. Would consume maybe 0.75 or 0.8 of an amp, right? That would limit our lights. Now we can add a bunch of lights because they're very efficient. And they're continuing, technology is continuing to improve, and you can add a lot. And the good thing about LED lights is that the LED lights don't heat up like the incandescent light bulbs. They do not heat up at all. And the only downfall of LED lights is the light is very white.
Yeah.
Very, very bright, and it kinda hurts your eyes. Incandescent lights were a little bit softer, but they're working on new technologies to make sure that the lights are better for our eyes, right? But LED lights actually consume very little amperage, so that's why you can put a lot of lights. Now, because I can put 169 lights, that doesn't mean that I'm gonna put 169 lights on that circuit. If I'm going into a house, right, and I can put 160 lights into a house, I'm not gonna put one circuit for that house. I'm gonna put at least a minimum of 2, because if one of the circuits fails for any reason, I want the customers to at least have a little bit of light in the house, right? Some light. So just because I can put a bunch of load into a circuit, that doesn't mean that I'm gonna install it. Because as I become not only a person that runs wires, a person that installs boxes, I evolve into a person that understands electricity, and also I become a designer, right? You go ahead, you understand circuits, and you say, okay, so I know I can put 100 lights here, but I'm gonna go ahead and stagger them, so if one of the circuits fails for any reason, the customer still has lights as an emergency around their house. So for us, the minimum amount of circuits that we put in a house is 2. So we'll stagger the lights around the house, and we'll make sure that the customer has at least 2 circuits for lights. Because of, anything could fail, the panel could fail, everything is man-made and something could happen, so we wanna make sure that when we design our circuits, they're effective. They're not only something that you, okay, let me go ahead and put on a switch, put it on a box, run the wires, and it'll turn on the light. I need to make sure that my circuits are effective as well, okay? So going back to what is a parallel circuit, our amperage adds up. So whenever we have a load, we need to know what load is going to be on that circuit. So for example, on that receptacle over there, we have a microwave and we also have a refrigerator. So both of those loads are on the same circuit. The microwave uses about 10 amps, and the refrigerator, on the front of the refrigerator, it says 600 watts. So I know that both of them are connected to 120 volts because they're plugged into the receptacle, right? So on one, I know what's the amperage that's being consumed, and I know the voltage. But on the other one, it only tells me 600 watts. So if you guys use Ohm's law, how many amps are being consumed by that refrigerator? you're taking 600 and you're dividing it by
Fine.
120, right? 600 divided by 120 tells me, it gives me how much?
Five.
Five.
Makes sense.
5, right? Okay, so if the refrigerator is using 5 amps and the microwave is using 10 amps, when both of them are on at the same time, how many amps are flowing through that circuit? 15 amps, right? Now, the code tells me that for certain receptacles in a house, they can't be 15 amps. They have to be 20 amps. That gives us a little bit more amperage capacity because in parallel circuits, all of the amps add up. So the more loads you put into your house, you connect your phone here, you connect also your Xbox, and then you go to another receptacle in the same living room, but those receptacles are on the same circuit, right? And then you go ahead and you connect the vacuum cleaner. Sometimes people will say, oh, I just turned on the vacuum cleaner and the breaker tripped, and I don't know why. I just turned on the vacuum cleaner. But they didn't know that on the other side of the wall, somebody had a heater on. That heater was on with 13 amps. Your vacuum cleaner turned on with 8 amps, and your circuit was only 15 amps. So what did the breaker do? It turned off the circuit because too many amps were flowing and it was overheating the breaker, okay? So this is what happens when you wire a circuit in parallel. All of the amperage adds up, and our constant value is going to be the voltage, all right? Now, all of our circuits, if we wire them in series, or if we wire them in parallel, they're going to be running together, always. If we're using Romex, for example here, we have 2 wires that will complete a circuit. We have our current carrying conductor, and we have what we call a neutral. And then this wire right here is only for safety. This is to be able to ground every metal part in the circuit. So in this wire, which is called a 14-2, we have the wires that we need to complete a circuit. In this wire right here, which is still a 14, we actually have an extra wire. So we have a red wire that can be used as a current carrying conductor, a black wire that can be used as a current carrying conductor, a white wire that is only to be used as a neutral, and our bare wire that is used for safety to be able to ground every metal part of the circuit, right? This is a 14-3. This is a 14-2. So we're limited in our colors. We only have red and we have black. So there's no blue, there's no pink, there's no yellow. These are the only colors that we have for this type of material. And the manufacturer, in order for us not to make a mistake, because it's kind of hard, unless you are very familiar with wires, you can feel the difference between one conductor and another and the thickness of it. They made sure that we understand which ones are different. So these 2 are 14, and then we come right here with the number 12. So we go with a 12-2, which is the same concept, right? Of the 14-2, we have 3 conductors. 1 black conductor that is a current carrying conductor, 1 white conductor that is a neutral, and we have a bare wire that is for safety, right? This bare wire is only for safety in this Romex. Then we have our 12-3, and it's the same concept. We have a red wire, which could be a current carrying conductor, a black wire that could be a current carrying conductor, a neutral, and we have a bare wire that is for safety to connect every metal part of the circuit. And we go further to larger wires. So for example here, we have a number 10. We have a 10-3. This 10-3 has a black current carrying conductor, a red current carrying conductor, a white as a neutral, and we have our bare wire for safety, right? But this one, what capacity do we have in amperage for a number 10? 30 amp capacity for a number 10, right? Now, where do we find that information? Where do we know? How do we know that it's 30 amps? Where do we find that info? In your table, right?
Yes.
In the table that I gave you, that gives you the amperage capacity of each conductor that is allowed for you to use in an electrical circuit. Okay? So you guys have a table. If I ask you what is the amp capacity of a number 10, or if I ask you what's the amp capacity of a number 8, you guys should be able to find it in your table, and it tells you what's the amp capacity of a wire. So all of this information is out there for you guys to know what size of wire you're gonna use,
A la 1:30.
right? Okay, so this one right here is a number 8. As the wires get larger, now we use stranded. You guys used stranded yesterday, right? As the wires get larger, we use stranded because that makes them a little bit more flexible. As the wires get larger, if they're solid, it gets really hard to be able to bend them, to be able to make a hook, to be able to fold them in the box. So what they do is that they make them stranded, and the stranded is very, very flexible to be able to maneuver, and it's easier on your hands as well. So this is an 8-gauge wire, and this one has a 40 amp capacity, right? And we can go on and go on and go on with large and larger and larger conductors. And this is not the only method. We could also run our conductors in a raceway. When we have conductors in a raceway, now we have other colors that we can use, right? For example, here we have a blue, we have a red, we can have black, we can have pink, we can have yellow. We can have an array of colors that we can use to identify the use of each one of the wires, right? So this is how we would run them if we're using a raceway. And this would be a commercial installation. And Romex is what we use in residential installations, all right? So does anybody have any questions? Romex is what we're gonna be using when we wire residential installations.
When we in the railway, is in this area, we need a bare wire. The bare wire.
Adds up, and our power also adds up. So whatever the utility company is gonna charge us for anything that we use. So power doesn't change. Power in a parallel circuit adds up. Very, very important that we understand about our electrical circuits and how they are used and how they're wired. So let's go over there into the lab, and I'm gonna show you guys an installation, and I'm gonna show you parallel connections. Sometimes their magnetic fields, if they were close together, they would interfere with each other, but at a certain distance. But when you run them together, they actually cancel each other out, and the conductor doesn't heat up as much, okay? So when you guys are connecting inside of these boxes, we have to make sure that our wires are not too long and they're not too short, right? And when we're also connecting, we wanna make sure that we have good splices. Like I was telling you, we wanna make sure that our wires are well secured together, because if we have loose connections, see this splice? I think he has to work on this splice. It's not a good splice. And it's crucial because the inspector is not gonna take his time and go through each one of your wire nuts. He doesn't have the time to do that. But as a professional, you have to inspect your work, and you have to make sure that your work is up to par, and that none of the things that you do are gonna create an accident later on. Because when current is flowing through your wires, they're creating heat. And if there's a little bit of air in between, for example, when you connect right here to these screws, I always make sure that the wire can't move. This connection right here has to be very tight, because if there's a little bit of air, there could be arcing created. And that arc allows a lot of current to flow. Instead of only 0.89 amps flowing through here, that might go up to 6, 7.